Alrighty, so we are changing gears from the other day. I know I've explained away this lecture a couple times already, but it really is sort of a collection of odds and ends, but they do have a common thread, and it's a bunch of things about the Earth that don't really have another place to talk about them, or formally a place to talk about them. And I'd get into the middle of the semester or the end of the semester and say, okay, well, remember when we talked about... And you guys would just blink at me. And I'm like, oh, did I forget to mention? Yeah, you didn't tell us. Oh, crap. Okay. So little by little, again, this slide, this conversation has grown. These slides have grown. And like layers of the Earth. I can't tell you how many times we get to the end of the semester and I'd be talking about something and I'm like, oh, just, remember that layers of the Earth diagram. What? We never. So now that made its way into here as well. So... again, it's just a hodgepodge of things. It is broken more or less into three themes, all right? And we just left one of the themes, again, at the end of last lecture. Today, we're going to have one. And then we'll stop at a nice place to shift gears, and we'll save that for next Tuesday. Then we'll be done with this conversation. So, and again... we've got one topic after that, and then we're going to be looking at lecture test number 1. So it is coming. Not next week, but most definitely the week after. We'll see on Thursday of next week whether or not the test will be Tuesday or Thursday. I can't remember if I could do the history of environmental science in one lecture or I need a little more time. I can't remember. So... This is a cool little experiment, and I do encourage you to do it at home. Back when I first started teaching this, we didn't have flashlights in the classroom. Every so often somebody might have a little one on their keychain. I never remembered to bring one in. And now, you all are traveling around with these little pocket computers that have a flashlight built into them, and we could arguably do this, but then we'd have to close all the blinds and so on and so forth. So I ask you to, a little later, to try it at home with a friend. You'll need an assistant. But it's also something that you could do in your mind and probably get the same idea out of it. So you need a flashlight, sheet of paper, and a pencil, and a third arm, basically. What you got to do is, we actually start in the back here. I understand why they put that flashlight in the back, but it is the first part of the experiment. So you hold a flashlight over a table, 1.5 feet or so, just so your circle of light that it makes is about the size of a lid to a jar, okay? And you want to draw a circle around that circle of light on that piece of paper and notice the light's intensity. Then, want you to hold the flashlight at an angle. I'm not going to tell you degrees, enough to make it turn from a circle into a good-size oval. All right? And trace that too while you're at it. It's more about the light intensity than anything else, but it helps to draw the circles. And again, as you're drawing that circle, please notice the light intensity. Now, as I said, most of you guys could do this in your heads. It is still worth it, though, because it is a surprising difference. But what do you think happens as we turn this from a circle into an oval? What happens to the intensity of the light on the piece of paper? It what? It weakens. It decreases, right? And why is that? Somebody else. Why does the intensity of the light on that piece of paper decrease? Or you again, if you want.
It's covering the surface area?
What?
More
surface area, yeah. So the intensity of the flashlight, the batteries probably hasn't changed. Just as many photons are coming out of it in either situation. But you have the same amount of energy over a wider space, okay? And as such, then it's going to be dimmer. You may have tooled around, if you got one of those fancy flashlights that zooms in and zooms out, you may have noticed that when you do a fine focus beam, it's super bright. And as you get a bigger area, it's less bright. Well, duh, right? But it's important. And this is sort of an analogy here for the sunlight coming into the Earth's surface. Now, you might want to argue that at any given area on the Earth, you know, it's flat. Okay, I get that. It's a sphere. We're looking at small areas. Well, if you think a little bigger, all right, there are areas where the sunlight comes in much more directly, essentially flat. And because of the curvature, there are areas where the sunlight comes in spread over a much larger.
Oh, I like that. I teach radiology. I saw the word radiation.
Oh, okay.
Very good.
Solar radiation, a little different though, but not much. So the same energy spreads out over a lot bigger radius. Now, does that mean that it is less bright there than it is somewhere else? Well, no, not exactly. But we're talking about all the other energy that comes out of the sun, okay? And in this conversation, primarily, we're talking about heat energy. And what this tells us then is that in the areas closer to the pole, closer to the equator, we'll get to the poles in a second, closer to the equator, the sunlight is more concentrated. All right, you get more bang for the buck, so to speak, because it is hitting a flatter sort of surface. And as you move north or south from the equator, it becomes more and more diluted. They get less and less energy from the same sun. And that, my friends, is what leads us to our conversation about the seasons. All right, this all is because the Earth is tilted. You would still have less sun above or below, you know, because of the sphericity of the thing. But the fact that it's tilted, it moves it around. And different times of the year, as you're probably aware, we get more energy from the sun than others. You grew up hearing about how in the southern hemisphere, their seasons are reversed from ours. Well, this will show you why if you didn't quite get it. The amount of daylight versus nighttime. This diagram will explain. There is a deceivingly large amount of information that comes from this diagram onto test number 1. Okay? And I will try to be very blatant about what that information is. But just because we stay on one slide, folks tend to think, oh, well, there's not that much stuff. There's a lot of stuff on this slide. So it's a circle, it's a cycle. There is no beginning, there is no end, hopefully. But there is a logical place to... There is a logical place to start. In spring semester, I start at the December solstice. In fall semester, I start at the summer solstice. All right. Can anybody, just without even necessarily starting this conversation too much, what's a solstice? Or what happens at a solstice? What do we know about solstices? Solstice. No, that's not right.
Winter solstice, the shortest day of the year.
Shortest day of the year, okay. What else do we know? Winter solstice, shortest day.
Summer's the longest day.
Summer's the longest day, okay. What happens in between?
As we go from winter solstice to summer, the days get longer.
Yes. So I had to make sure that was, you said the right one before. I agree. Yeah, I actually had a student this morning, and I teach it this way, but I've never heard anyone answer out of the just cold answer like this. She said basically that as the first answer instead of everyone knows, or traditionally we say exactly what you said. Winter solstice is the shortest day. Summer solstice is the longest day. She said that after the summer solstice, the days start to get shorter, and after the winter solstice, the days start to get longer. And like I said, it's totally true, but it's unusual for you guys to make that jump immediately. So that's exactly where we need to end up. But we start with that factoid, though. And the factoid is that the solstices are either our longest or our shortest days. So when we start here at the winter solstice, all right, we're looking at December 21st. A word about these numbers. You haven't had a test of mine yet, so you don't necessarily know. You've seen me as a teacher, what, 4 times now? All of 4, maybe 5 times. But a test really brings out, who that teacher really is a lot of times. Sorry, my watch is going crazy. It's all those videos I just uploaded. I'm not one of those guys that's going to say, when is the fall equinox? September 21st, September 22nd, September 23rd. No. In fact, in here, we're going to normalize everything to the 21st, okay? Because there are variations. Things as simple as every 4 years, the leap year can throw it off. And sometimes these just aren't on these days. So, for sake of your memory, whether it's a solstice or an equinox on the test, they're all going to be set to the 21st. Kavish, you good? You just got to remember the month. And I'd like to think by now, you know that December gives you winter. June gives you summer, so on and so forth. So, you never know. Now, you are actually from Southern Hemisphere? Sir? Yes? No? Where are you from? Yeah? Spain. Oh, so you're not. Okay, I apologize. I was thinking South America. I apologize. So you're Northern Hemisphere as well. So maybe one person grew up with that not being true, but you're in the good hemisphere. Don't worry. So, anywho, at any rate, so you've known this, and you've also grown up, again, as we said a little while ago, noting that when we have winter, Southern Hemisphere has summer, and the seasons are reversed, and so on and so forth. So we're going to show you how all of that stuff comes to be. So, anywho, solstice. The sun is shining on 23.5. I neglected to point that out when we were here. It's small, but you see the equator there in the middle at 0. You see the 2 tropics. Tropic of Cancer, 23.5 north. Tropic of Capricorn, 23.5 south, right? All right, so they're not as easily seen on this diagram. So that's what those dashed lines are. Top labels it, nothing else labels it. We're over here on the left. So on the winter solstice, the sun's energy is concentrated on 23.5 south. That is why they have their summer then. We have our winter then. The majority of the solar energy is going down there. We also know that as our shortest day of the year. Now, my earth science class actually does a really cool lab. I don't think it's cool, but I think it's cool. Where we actually pull some actual data from timeanddate.com, and we look at the amount of sunlight each day and how it grows and shrinks and so on and so forth. Again, this is sort of based on your latitude, whether or not you get the exact right day for these things. Anywho, arguably, that is the shortest day of the year. From there, as we move towards March, towards an equinox, the amount of daylight starts to grow. Now, what do we know about equinoxes? Does the word even mean anything, maybe? No? Okay. Well, equinox, equal. All right. And nox is for night. So, technically means equal night. And this should be our days of 12 and 12. Right? 12 hours of sunlight, 12 hours of darkness. Again, varies with latitude, but that's what we always have learned. So, as we come from the winter solstice to, they have special words for your equinoxes. Spring equinox is vernal with a V. V-E-R-N-A-L. I'll never have you spell it, but I do want you to recognize it when you see it. Because we won't call it spring equinox on the test. As we move from December to March, which we're in the middle of doing right now, closer to the end than the beginning, I think, at this point, you're slowly but surely going to see the amount of daylight increasing. You may have noticed, hopefully, that it's not dark at 4:20 anymore. Okay? Thank goodness. I'm not a fan of winter. I'm not a fan of darkness. I know some people love this time of the year, and that's great for them. But I take a whole lot of solace knowing that on December 22nd, we had 2.5 seconds every day. It's small, but it adds up. 2.5 seconds every day of, 2.5 minutes. Yeah, 2.5 minutes every day of more sunlight. All right. And now we get to middle February, bless you. And it's right around 5:20, I think is when I was just looking yesterday, 5:15, 5:20. We've almost added an hour since December already. So we're getting there. We're getting there. So where's the sun shine on this here equinox thing? You in the back. Where's the sun shine on the equinox? Come on, guys. Help us out. All right. It shines on the equator. Equinox, equator. All right. Otherwise known as 0 degrees latitude. So we've moved 23.5 degrees northward. As we move from the equinox to the solstice again, they don't have funky words for the solstice. We just say summer solstice. All right. You're moving from the equinox up to 23.5 degrees north. 23.5 degrees north. And that is our longest day. And then, unfortunately, June 21st, summer's, heck, a year or two ago when you guys were in school, you were still in school by June 21st. From there on down, you're actually losing summer. You're losing daylight. We get back to the equinox. The sun is back down to the equator again. And there we move from the, that's the autumnal equinox, by the way, as in autumn, but we throw an O on the end of it. Okay, at least that one's not a completely foreign word for you. So autumnal equinox, not fall. So we move from the autumnal equinox to the winter solstice. We're moving from the equator back down to 23.5 degrees south. All right. So, and it just keeps bouncing back and forth between those two tropics. Again, you want to make sure you remember Tropic of Cancer is 23.5 north. Capricorn is 23.5 south. For the longest time, I had trouble remembering those. And then one day I noticed they're alphabetical. Let that be helpful to you. CAN comes before CAB. What else? The other thing you may have heard is that the winters aren't as bad in the southern hemisphere. Okay, yeah, it's winter there, but it's not bad. It's not the same, blah, 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 blah. Well, look where those tropics are falling. Okay, 23.5 south. Heck, you're down practically to bottom of South America. And if you spin that in your brain, you're down practically to the bottom of Africa. That's a lot more land that's in the tropics. You look up northern hemisphere, we aren't even to Cuba yet. And you're out of the tropic zone. So that's why our winters are so much different. There's other reasons too, but it's one of the big ones. One of the big ones. All right. Let's see. We got the equinoxes. You know that they're vernal and autumnal, not spring and fall. You got your solstices. You know the dates, the months. You got your tropics. You got the 23.5. Why is the 23.5? The 23.5 is because of the tilt of the Earth. Okay? If we were tilted 33 1/3, well, then the tropics would be at 33 1/3 north, 33 1/3 south, or whatever. Or if we didn't have a tilt, they wouldn't exist. Or they might be a barrier on the very outskirts, much closer to the equator at any rate. The sun would always shine most directly at the equator. So the reason for all of this is because of the Earth's tilt. Oh, last thing. How many seasons are we looking at here? 4. How many months we got? 12. How many months per season is that? Mathematically, at any rate, yeah. Yeah, there are places in the world where that's true. Just not here, unfortunately. Well, I actually meant to talk about that. Looking at it's more because of the tilt. If you look at this the way you can see exactly how, because that's still, and I'm an earth science teacher, and I'm still like, wait, why does that? But looking at this picture, you can see why. They're tilted away. There's no way they're ever going to get that sun. You know, even when it spins, it's just out of the range. So yeah, that's exactly what's going on. And I don't usually talk about that, but for some reason this morning, I said it, and I'm like, oh yeah, that's why. Because like I said, I found myself, processing that as well. It's got to be weird. My son was up there when they were in the all light stage. He wasn't there for the all darkness. And he says it was really strange. 11. It does get dimmer, and they get like a weird, funky sunset. But 11 o'clock at night that the sun's still essentially up. It was really strange. But they get used to it, I guess. And again, if you grow up in it and so on and so forth, you're just, I suppose your bodily systems adjust themselves. But to visit, that's got to be really interesting to get used to.
I know some places, instead of 4 seasons, they have dry season and wet season.
Yeah, that's something. We'll actually get, we don't exactly get to that, but when we start talking about climate zones and stuff, a little more so into the later chapters, we'll talk. They're definitely controlled by precipitation more than temperature. There's a weird little triangle where we show, I think it's latitude, temperature, and precipitation, and you can plot various things on that 3 things there. Because it's warm all year, no matter what. It's not a function of warm and cold. And it is just that. It's when they get water and when they don't get water. So, yeah, there's a lot of, I don't want to call them stereotypes, but generalizations that we make. Some parts of the world, it's completely different. And that's one of the cool things. That's why I like this class. We get to talk about, for me at any rate, some of the different things that guys don't necessarily walk into this door knowing. Except everyone then goes back to Lion King, and they're like, oh, yeah, the wet season. I know that. And so we tie it in somewhere. Tie it into something. That's great. You guys are finally waking up and talking a little bit. What else we got? Anything? And we'll switch slides otherwise. Okay. So again, the more you guys input, the less it's just me sitting here talking to you guys or standing here talking to you guys. So if you're getting bored, it's your fault. No, I'm kidding. I'm kidding you. All right, so we are switching gears now. We talked about the solar, and we will get, in this class, we do get into incoming solar radiation a little more so. I get it in my earth science. We do it under the meteorology. You guys get it for exactly what we were just chit-chatting about, climates. So we'll touch on that one again. So now we're switching gears. We're going to talk about some inside of the earth stuff. But before we go there, we're going to mentally go back to that very first slide when I was introducing this and you guys were staring at the picture of the globe, right? And I said, what's the blue stuff? What's the green stuff? And you guys had all the right answers, and that was great. We're just formalizing that a little bit, and if you don't already for some reason have the words terrestrial and aquatic in your vocabulary, we'll give them to you. terrestria, terra firma. Okay, that is land, that is earth. Extraterrestrial comes from this word as well. Okay, from beyond, above and beyond, terrestrial. You notice that we were mostly a blue planet when we looked at that picture, okay? Nearly 3/4 of the Earth's surface is covered in oceans. Just about 1/3 of it is land. So, nothing new or, mind-blowing here. Just want to remind you before we move on. So, moving into that Earth, we've got a diameter of about 4,000 miles. Diameter, there's no math requirement for this class, so I'm obliged to remind you the difference between radius, diameter. Did I say diameter of? It's a radius of 4,000 miles. Remind you the difference between radius, diameter, and circumference. Okay? What does this radius of 4,000 miles mean? That's from where to where? One end to the midpoint. What would an end be? All right, so just some random spot on the surface of the Earth will work.
Surface to the middle of the Earth.
All right. Yeah, and again, we got that little squiggly there, which means approximately. That's the tilde sign, they say. Mind you, if you're at the top of the tallest mountain, the bottom of the lowest valley, it's going to vary. And you wouldn't think it's going to vary that much, but 4,000 miles isn't that much. I asked Siri just last lecture, not that we make this journey regularly, but from Manhattan to LA is 2,700 some miles. So it's not even twice that distance, and you're at the center of the Earth. Not that you could get there. That's a whole nother conversation. So what would diameter be then? Let's just remind ourselves of some basic math here real quick.
8,000 miles.
Okay, so diameter is twice radius. Circumference, I don't want a number, but what does circumference measure then in this case, in this conversation? It's one more sort of related word. Yeah. So if you needed to put a rope or a belt around the equator, that one's the circumference, and that's a totally different number. Now what? Circumference is at pi r squared. It's been a long time. They're connected. They're all connected. Okay, God bless geometry. But again, we're not doing math in here, but we're just, pointing out the differences where they are, pointing out some similarities where we can. But what I want to focus on is the fact that 4,000 miles is not that far. That was a weird beep. And guess what? Of that 4,000 miles, we've been from like here to the mall, straight down. Yet, all this stuff, you guys don't get so much in geology. I spent all this time talking about, the what's going on in the mantle and the core and we've been 2 miles. How the hell do we know what's going on there? Well, as you probably know, there's a lot of indirect ways that they can assess these things and model these things and think about these things. When we get there, and will we find out something a little different? Quite possibly, okay? I'd like to think we're not going to be completely wrong, that there's fine-tuning to be done, of course. But a lot of this is indirectly figured out. Heck, even with our mining equipment, we've only gone 7.5 miles. Now, I don't update these every semester. There are new breakthroughs. There are new changes. Humans, that's not going to change a whole heck of a lot. If you've ever been flipping through the channels and you stop by Discovery or National Geographic and you see these poor souls coming up out of diamond mines in the middle of Africa or something like that, they weigh all of like 75 pounds and they're wearing a towel because it's so hot down there. We're not going any farther unless we get these special suits and so on and so forth, okay? But drilling, we'll probably keep getting deeper and deeper. Yeah, you had a question or a comment?
Do you know where they drilled 7.5 miles?
Not off the top of my head, though, no. We've got a variety, whether we're going for oil or gas or just even exploration. And a lot of that, I actually have a buddy who's out in, he's off of Brazil, in the Gulf of Mexico, but he did some land stuff as well. A lot of it is slowly, sort of diagonally down in as well. We don't go straight. I think it's friction on the bits or something like that. I don't quite get it. But no, I don't know where we've been 7.5 miles. I could probably figure that out easily enough. But yeah.
It's in Russia.
Is it in Russia?
Yeah.
Okay. You seem quite proud of that. I see the smile on your face. What were they? Did you happen to know what they were drilling for? Was it just exploratory, or?
I think they were just exploring it. They only stopped. One of the main reasons they stopped is because it got so hot.
Yeah, I'm sure. It does. And we're going to actually talk about that, the geothermal gradient, here in a couple minutes. And that's one of the reasons, even when we're going 2 miles, with these, it's unbelievable. And we could build these amazing alloys and so on and so forth, and diamond-headed bits. And like I said, I think that's in there as part of the reason why we go diagonal. I don't know the connection, but somewhere in there, it's lower stress. I'll have to pester him. Right now, we're going back and forth about the current administration, but we're still buddies. So I will, one of these days, I'll talk to him about that. But yeah, so the point is that of that 4,000 miles, that's like getting on that road trip we just talked about from L.A. to Manhattan, or Manhattan to L.A., and stopping in Hoboken to pee. Okay, I mean, it's just, you barely started the journey. So we don't really need these mile comparison thingies, but I was just throwing this up there at some point. How many miles did you come to get here from Spain? Do you remember? Yeah. Too many. Yeah, there you go. And yeah, kilometers you probably know anyhow, not miles. So, yeah. You may have come 4,000. You could have gone to the center of the earth instead. So how do we know about this stuff? Okay. Well, this is something called the Mohorovicic discontinuity, named after Bob Mohorovicic. Well, Professor Mohorovicic. We shortened it a long time ago, not just me, everybody on the planet, to the Moho line, much to students' excitement everywhere. They did not have to spell Mohorovicic, let alone discontinuity. What this is the boundary between the crust and the mantle, all right? And again, how do we know this? Well, at one point, you guys probably are aware, we started blowing up a whole lot of really, really big bombs, okay? And because of things called seismographs, you guys know what a seismograph is, or at least have a general idea? Okay, it's those machines that they screw into the ground. Usually you see them when earthquakes happen. That pen bouncing up and down on the paper. Because we've got those all over the place, not just in America, but all over the place. We started to realize that when we blew up these bombs, the whole damn planet was shaking. Probably could have guessed that. They're big bombs. What they didn't quite process at first was that they weren't all receiving it at the same time. Yeah, there's distance and so on and so forth, but it was weirder than that. Something was happening. Now, again, we weren't completely ignorant. We knew that the inside of the earth was molten in some way, shape, or form. Why? Well, because every so often the earth cracks open and starts bleeding, right? We've got our volcanic events. We knew that. They've known that for thousands of years. We see volcanoes, something's going on. But they were able to, over time, piece this together to find out where that boundary actually was. And this Professor Mohorovicic was one of the key players, or at the very least, he got his article published first. Now, you're going to see a whole bunch of stuff on here. I don't want you to worry about the numbers, but I do want to talk about, you see the words velocity in there. What's happening is that the speed of these sound waves changes when you go from the crust to the mantle. And I without really thinking, I asked them this morning. I said, well, what would be easier to travel through, the solid rock or the molten rock? And they kind of blinked at me for a minute, and finally somebody said molten. And I'm like, that's the wrong answer, but I asked the wrong question. Okay? Your people, you can't walk through any of that stuff. If you really had to, sure, you could walk through molten rock. Okay, maybe, because it's not solid rock. We can't get through. So I rephrased the question. if you were running along on the surface of the earth, what would be better for you, a paved road or a muddy trail? And you guys, of course, would say a paved road. It's a lot easier for these energy waves, the seismic waves. That's what they call it, a seismograph and a seismologist and all that. It's all that size. That's those energy waves. It's a lot easier for that to travel through solid rock because it's consistent, it's solid, cohesive, than it is to travel through the molten stuff. So what happened when it hit the mantle, they would slow down. Take a little longer to get here, there. And that's the geometry. Again, we don't need to get into the nuts and bolts of it. But from all of these angles and whatnot, they were able to say, okay, it slows down here. And we noticed that across the planet, it slowed down at approximately the same place, all across the planet. And that came to be known as this discontinuity, or just much easier, the boundary between the crust and the mantle. All right. So that's what the low velocity, high velocity garbage is. We're just saying that those sound waves move slower through molten material than they do in solid. And you know that from just even your own experience. You might not have processed it at this level, but think about the last time you were in a pool, okay? And you're talking to your friend, you're up on the deck or whatever, and sound waves. You hear them just fine, okay? You jump down into the water, you're underwater, someone's talking to you, or the music's playing, it's all... Those sound waves are hitting the water. They're traveling much differently than they do through the air. It's the same idea. Right? Same idea. I don't know why this one turns into a click as you go thing. None of the other ones are. All right. Same idea, slightly different topic. Internal heat. So generally speaking, the Earth's heat comes from radioactive decay. Radiation. Now, when you guys think of radiation, 9 times out of 10, you go immediately to that bad stuff, the uranium, the bad cancer mutations, da-da-da-da-da-da. Yes, that is a thing, and that is a horrible thing, don't get me wrong. But what you don't necessarily know or think about is that everything around you is decaying all the time. Okay? Everything is decaying and giving off energy. Just it's not that all of it is bad. It is all heat, though. But generally speaking, you don't notice it because of all the other stuff that's going on around you. In the Earth, however, the Earth is much like a cooler that it's insulated. A lot of that radiation heat stays there. And that's something else you don't think about very often. A cooler, we only use it to keep stuff, cold, right? You could very easily use a cooler to keep stuff warm. The same ideas that keep stuff cold would keep stuff warm. It's just that they're oriented the wrong way. Somebody out there makes a horizontal cooler that a grandma or a soccer mom can put a casserole into and get it to its destination. You make a lot of money. I get a cut if you ever do that. So at any rate, the Earth is an insulator, and that energy stays in there and builds up over time. When you get down all the way to the core, you get that 4,000 miles down in, it is, they figure, approximately 9,000 degrees Fahrenheit. Now, we gave you a vocabulary word the other day for the temperature change as we go into the atmosphere, right? We had the lapse rate, remember that word? And it was some, per feet, it was this many degrees decrease. Well, now we have geothermal gradient. This is going into the Earth, and it is for X number of feet an increase. I'd like to think if you did the math, we would end up at right around the right number. I've never done the math. We got 4,000 miles. We got 1 degree Fahrenheit for every 70 feet. Maybe some of you could do that in your heads. I certainly can't. I also think it's probably exponential at some point, right? I don't think it's going to be a linear kind of transition. It's got to start compounding. Now, that's not 100% true. Anyone here ever been in a cave? A couple of you. Good. Are caves warm or are caves cool? Cold, cooler, yeah. And they're arguably in the ground, right? So this doesn't necessarily kick in right away, this geothermal gradient. There is sort of an ambient subsurface temperature. It's right around 58, 62. Again, the number is lost in my brain somewhere. That's the reason basements are typically quite cooler. Okay. Now, in the in the wintertime, you go down, your basement's really, really cold. That's because your basement is not completely under, you've got that, 1.5 feet or so, depending on how your house was built, that is exposed to the actual air. You don't have the insulative properties of the earth, but arguably it should still be warmer than outside. But if you had, excuse me, choking a little bit here, very traditional old root celery kind of basement that is completely underground, it should stay more or less the same temperature all year round. The other exception is when the hot comes to us. Every so often, bits of magma will work their way kind of through cracks and crevices up towards the surface. And again, they manifest themselves as volcanoes, or sometimes they just stay under the Earth's surface and make things like Yellowstone Park, where you've got your geysers, the groundwater heated up, or something called hot spots. The Hawaiian Islands is a chain of volcanic islands. You might have heard of it. This hot spot is this giant pool of magma, unusually close to the surface. Okay. But those are exceptions to the rule. Generally speaking, temperature gradually increases as you go in. Questions before we start anew? All right. This is a pretty classic image here, huh? Even the colors bring you back to your youth, probably. I know they bring you back to mine. These are very late 70s, early 80s. The only thing we're missing here is avocado, and they've got that in the continent almost there. So, but this is a really classic third grade kind of crust mantle core. Okay, well, in high school, hopefully they added the fact that there's the inner core and the outer core. You learn that. We're going to take that a little further in a little bit, but in the beginning, we're going to talk about just those three things: the crust, the mantle, and the core. We're not going to get into rocks in environmental science. So don't worry if you don't know what basalt or granite is. I'm not going to quiz you about it later. Suffice it to say they're both igneous rocks, which means they're both made out of magma or lava. Okay, in this case, magma. And what's more important is that they're made up of two different rocks. The ocean floor, and that is crust, is something called basalt. The continents themselves are something called granite. And what's more important, and doesn't make an appearance yet, you guys will never see it, so I'm going to tell you, is that those are two different densities, which is why the ocean floor is lower, or more so why the continent is higher. If you go and you erase all of the history and go all the way back to very, very, very near the beginning, before there was even water in the oceans, because basalt is more dense than granite, it sat a little lower. And for the same reason why when you push down on something, something else bounces up, well, that caused the continents to rise a little. As water did start to fall and the ocean floor sank even more, that buoyed up the continents that much more. That gave us the, disparity is a strong word, but that gave us the difference, I guess. Okay, and why the oceans are where they are and why the continents are where they are. Please don't worry about these distances, thicknesses. I have other numbers that you do need to know. We're not going to worry about these, but just in case you wondered, they're here. Now, some of you that have been up north and saw in the mountains, some of you have been other places and you've seen rocks sticking out. You're like, that was sandstone. That was limestone. There was no granite there. There's no, you haven't been to the ocean floor, but if you did, you'd say, I don't see basalt here. There's all this sandstone and mudstone here. Yeah, there's thousands of feet, hundreds of feet, we'll say hundreds of feet to be safe, of sedimentary rock on top of this stuff. These are the cores, the roots, okay? Sediment piles, just like dust on your shelves at home, okay? Dust accumulates at the surface of the earth. Sediment, we call it, not dust. And that is built up over time. But when you go down underneath that layer of sediment, you see the basalt, you see the granite. All right, beneath the crust, we've got the mantle, the chewy nougat. A ways back, I don't know if it was when I was in college or when I first started teaching, they used to refer to it more like Play-Doh or clay. But at some point they switched over to silly putty, and you're probably saying, well, both of those are silly. Why would you even say Play-Doh or silly putty? Well, again, they want to give you, and we're teaching this at younger and younger levels, we want to give you something that you can compare it to, something that makes sense. So why change from Play-Doh to silly putty then? Well, silly putty, if you remember, if you've ever had the opportunity to play with it, hopefully you have, is bouncy. It's elastic. And again, we haven't been there, but from the tests they've been able to do, from what they're seeing, there is some, not only is this material malleable like clay is, but it also appears to have these elastic properties. So they've switched gears, and now they ask us to refer to it as a silly putty-like consistency. Now, of course, the scientists say malleable and elastic, but it's a 100 level class, so we're going to say silly putty. Okay? All right. The mantle is not consistent. The mantle does have density changes in it. In other words, some places it's thicker, some places it's thinner. They've divided it into 3 portions. The upper one we find interesting because of something called plate tectonics. You've probably heard about it. The middle, And the lower mantle, yeah, they don't really care about the lower mantle that much at all, but some folks called geophysicists love all of that. And bless their hearts, because nobody else cares. So, so the mantle isn't consistently one thick thing, and it's not entirely molten. We try not to use the word molten. We know when we see lava come out at the surface, all right, it's definitely fluid. 9 times out of 10, there's thick lava, don't get me wrong. But remember pressure. Okay, pressure does amazing things. Have any of you ever shaken one of those little green gas grill bottles? Well, you should. It won't blow up. Trust me on this one. Next time you're at Targets or Walmarts, go shake one. Those of you that have shook one, what's inside of it? What's it sound like is inside of it? Well, there might be a little ball. Spray paint cans definitely have a little ball. But no, I'm going for something simpler than that. What does it sound like is in there when you shake it? All right, you guys all now have homework. It's liquid, okay? If you ever seen at gas stations, the sign says LP gas, it's liquid propane gas. That's what LP stands for. In that canister, it is a liquid. Now, I assume you've been around a gas grill when it's on. When you plug in that sucker and turn on the little dial, what happens? It goes shh. What's coming out of there? A gas. That's what pressure does, okay? You pressurize a gas, it turns into a liquid. You pressurize a semi-solid, it gets semi-solider. So, when we see this lava come out at the surface, that's not what it looks like inside the earth, okay? It's under more pressure, it becomes that silly putty stuff. But seriously, go shake the gas can, you'll be surprised. It definitely sounds like there's liquid sloshing around in there, because there is. It's a pressurized canister. All right, moving right along. The core. As we said, it's not just the core nowadays. We got to talk about inner core and outer core. And I told you probably on the first time we had this conversation that this little factoid here is probably one of the main reasons we're actually able to sit here and talk about it now. The outer core, rotating around the inner core gives us a force field we call the magnetosphere, which filters out a lot of nasty radiation from the sun. And again, not even arguably speaking, totally truthfully speaking, if that magnetosphere had not formed at some point, we would have life the cell, think about what radiation does to cells. We would have, if we evolved, would have been quite different things. I don't mean if evolution, if life had ever gotten started because of the radiation. I'm not going to talk about the origins of life, but it's important. Now, what I don't quite get, and I'll be honest with you, geophysics is, I do surface processes and critters. That's why I'm able to teach this class. Okay, geophysics is far from my realm. The whole, if you talk about the outside of the Earth makes total sense. Solid, we're exposed to the atmosphere, it's cool, solid rock forms, I get it. The mantle, okay, we're inside, it's heated, it's insulated, we could be molten-y, plasticky kind of stuff, that's fine. And then all of a sudden we turn into a liquid metal, and then we go to a solid metal? And again, I get the whole temperature thing, it gets hotter as we get in there, so the liquid metal makes sense, but then why does it change to a solid metal? I don't know. It's probably pressure and those gas laws that I never quite fully learned in chemistry class. It's both primarily iron, a little bit of nickel and a few other things thrown in. The reason it's there is because of something called density separation. You're all familiar with density separation. It's the reason why the last time you had a glass of orange juice, you probably shook up the jug before you poured the glass. All the thick stuff settles out to the bottom, all the pulp and the whatnots. In a sphere, the bottom is the center, right? So that's where all the heavy stuff went. So it makes sense that that's where the iron is. And again, a handful of other heavy metals. But that liquid solid, that always gave me reason to pause. Questions about the core? Okay. So if you read about stuff like this, you may have come across some really strange stuff. Oceans in the mantle and so on and so forth. Jules Verne aside. There's some folks out there studying some pretty crazy stuff. And they're, as always, quite confident in their findings. And I'm sure they are. Lord only knows what we'll find in there. Pockets of diamonds and crystals and so on and so forth. They say there are these oceans in there as well. We probably will never know. Talking about the whether we're drilling in Russia or drilling in the Gulf of Mexico or sending people into mines in Africa. I really think due to constraints, it's going to be a long, long, long time before we could go any farther than we have gone. Upwards and outwards into space, yeah, we could overcome that actually a lot easier. It's going to be tough to design something that could stay intact, maintain some habitable conditions, and go into the Earth for any distance. So... But who knows? We've got little robots driving around on Mars and on the moon, and we've got robots circling other planets. Call them droids, call them whatever you want, satellites, rovers. But they are, little machines going out exploring for us. We will probably get one of those in there, but even that, I think, our silicon would start to melt and all of that. It's just, into the Earth is a tough one. Really, really tough one. So it's college now. We can't just keep it crust mantle core or even crust mantle core. We got to kick it up a notch. And I'm sure you guys did this in high school. You learned about the lithosphere and the asthenosphere when you took earth science. I'd like to think. Again, please don't worry about these depths. They're just there for your learning leisure. These are important because of plate tectonics. And you may have had your teacher or whatever say, well, the crust is broken up into plates and it floats on the mantle. Sort of true. Technically speaking, we need to say that the lithosphere is broken into plates and the lithosphere is floating on something called the asthenosphere. What's the difference? Well, the lithosphere is the crust plus a little bit of the mantle. If you're trying to picture this, next time you crack an egg, you know that little bit of goo that you just can't get off the shell no matter what you do? That's that little bit of asthenosphere. So the shell and that egg goo, that's your lithosphere. Okay? And that's floating on resting on the middle mantle. Remember we said the middle mantle would be sort of important? It's not the rest of the mantle. We still got that lower mantle that really nobody cares about. But we're on that middle mantle right now. So you've got this lithosphere cracked into pieces. We'll show you the pieces in a minute. And that's resting on something we call the asthenosphere. Plate tectonics we don't really get into in this class. Again, you know it's important. It explains why a handful of phenomena happen: earthquakes, volcanoes, where mountain ranges are, current location of the continents, previous location, future location, all that stuff. But there's so many other things to talk about that we just tend not to talk about. If we run out of stuff by the end of the semester, we'll do it, but I doubt that'll happen. So we're going to modify that lovely little diagram. You can see now this is my attempt at a diagram because we don't have any continents on here. The right side of this is those old school, the crust, mantle, core. The left side, we've added the two new terms, the lithosphere and the asthenosphere. So let's start by looking at the left side. And with that in mind, what do you think A is pointing to? The lithosphere. Good. All right, so B must be that asthenosphere. We're not going to go alphabetical anymore. We're going to go back to the surface of the Earth. What's D pointing to then? What would we call that? We've already used lithosphere, so D must be pointing at what do we call the surface of the Earth? The crust. All right, C is the no, that would be E down there. Yeah, C's pointing to hopefully to the middle of that orange there. I'm looking at it at an angle, but yeah, it's hard to tell. Is it where the arrow is pointing or where the arrow ends? That's always tricky. But no, C is supposed to be the mantle. Inner core is, help them out, guys. Oh, then what's outer core? Which one's on the inside? Which one's on the outside? Yeah. Inner core is E. Inner core is on the inside. Outer core is AB. All right, this is a tough diagram. So let's run through this again. A is lithosphere. Good. B is good. C? C just mantle. Man, you'll have a list of vocab off to the side, so it won't be so much guesswork. C is mantle. D is crust. E? All right, and AB, outer core. You may be wondering why the hell AB and not F, right? You guys just got out of 12 years of standardized tests. You tell me, how many choices do you get on a Scantron? 5. You would not believe the amount of stress it causes to watch you guys, to watch your faces as I make you color in 2 dots in one row. You'd think the world was going to collapse. But yeah, so if I wanted to have more than 5 choices, I had to move on to AB or AC. That was really weird because you're like, wait, they're not even next to one another. I hand graded when I used those Scantron sheets. I hand graded them, so you could do that stuff. Yes, it would have made the computer freak out if you colored in 2 dots in one row. But again, it's okay now, and especially to the online folks because they still. Are taking a computer test, arguably, but that one I could make, E and F and so on and so forth. So they still get, this is basically just an old test diagram I colored in. But, yeah, so that's why AB. But, and we need to talk about how we're going to do testing in here, too. We're going back and forth between the online testing and good old-fashioned paper and pencil. we get a little closer to the first test, we'll talk about that. What you guys want to do and what we end up doing. It's not exactly a democracy in here, but we like to pretend every so often. So right here, and I've told you a couple times now when stuff is, blatantly, hey, this is on the test. This is on the test. All right, so that's why I took the time to make sure that you got what you got there, because we don't want you messing up something as simple as the layers of the Earth diagram. That's 6 points right there. Just like we told you the other day that the positive, negative, neutral stuff for the protons, neutrons, and electrons. Remember that? The lecture that you watched while I was in Maryland. There's 9 points right there on the test as well. If you've been keeping track of all the answers I've told you, you're up to about half the test so far that I've told you exactly what's going to be on it. So hopefully you're keeping track. That being said, does anyone need any of these letters again, or we got them all? Okay. So, plate tectonics is important, and in my other classes, we do eventually get to it if we have time. It's weird. Plate tectonics, our understanding hasn't really changed that much in decades, but the importance that we place on it has changed. For years, it was like the last chapter in the book, and like I just sort of half-jokingly said, if we get to it, we get to it. And it's moved to like chapter 2 in all the geology and the earth science books now, because they've sort of reversed the way they talk about it. We used to say, okay, we talked about earthquakes, we talked about volcanoes, we talked about this, that, and the other thing. This is responsible for all that stuff. Let's learn a little bit about it. Now, they preface all of that with talking about plate tectonics and then saying, okay, we'll give you some examples later on in the semester about, things that are caused by it. And again, in here, it's still important because when we talk about these cycles, we'll talk about a little later, the carbon cycle, the nitrogen cycle, all of these various nutrient cycles, a lot of that is totally driven by plate tectonics, but there's so many other things to talk about. We don't, like I said, just dedicate it. And in all honesty, the 6 different ways a plate can move, it's irrelevant right now. Okay? Later on, sure, there might be some point in talking about it. So we give it 5 minutes now. And if you never hear about it again in this class, at least you've had, this bit of introduction for it. Continental drift. Over the years, I've still heard a handful of you say, yeah, my teacher talked about continental drift. Hopefully only in a historical sense. Okay? I was in school in the 80s. Plate tectonics had not made it into the textbooks yet. There's that old joke about, how outdated textbooks are. It used to be a lot more true. Nowadays, you guys, maybe 5 years at the most. We had some pretty old books. Plate tectonics has been around since the late 60s. So there's no reason by like 85 it shouldn't have been in the textbooks yet. But it, at least not in ours. But continental drift was kind of self-explanatory. And I'm assuming you guys heard a little bit about this in earth science. So you had Alfred Wegener, and he did cartography. He was a geography guy. He was also a meteorologist. Okay, he was a Renaissance man, so to speak. And because of all that stuff, he went around on boats and saw a whole lot of the world. And again, you've probably heard this story, how he realized that bits of it looked like they literally fit together like pieces of a puzzle, and so on and so forth. And he had these amazing ideas and all kinds of data to support it. When you put these continents back together, the mountain ranges lined up. Not only did the mountain ranges line up, there were the same rock types. And not only were they just the same rock types, heck, they even had the same fossils in them. Literally, these were exactly the same environments when you put them back together. He had the unfortunate luck of presenting this to a bunch of geophysicists who even back then were all about the math. And they're like, Al, great, but how's it work? He's like, well, I don't know. I'm still working on that. And they're like, what? The continents are just floating through the ocean? Hence the continental drift, I guess. I wasn't there, but you get the idea. And it just went nowhere because he didn't have a reason for it. He couldn't prove, yeah, that looks cool, but how's it happen? And that's as far as it got. Well, come ahead a couple decades and we get our wonderful magical yellow submarines and we start traveling the ocean floor and we find these places where new ocean floor is being made. We go other places and we find out that there's places where the ocean floor is being destroyed, and we realize that we're living on conveyor belts, essentially. And then we figured out that those conveyor belts could be carrying these continents around. Nowadays, we jump ahead a few more decades, we've got GPS systems literally drilled into the ground, to the top of Mount Everest, the bottom of Death Valley, all over the place. We know without a question that these continents are moving. We know what direction they're moving, how fast they're moving. We know all this stuff. So, and they think they know why. But because we have all of this evidence, and again, it's a slightly different sort of mindset in science nowadays, a little bit. Plate tectonics it's no longer a question. They're still working on, will they ever find out exactly? Who knows? I told you that a little bit ago that the asthenosphere was important. It's convection that they think, convection currents. Okay? Things get hot, they expand, they rise, they get cool, they sink. And that makes these little wheels on that conveyor belt that I mentioned. Okay? But they're arguing over whether or not that lower mantle, I told you nobody cares about the lower mantle. Maybe they think there's bigger cells down there driving the regular size cells in the asthenosphere, and they'll keep themselves going in conferences for God knows how long. That's great. They'll have jobs. Okay? But that's where it is. Okay? But there's not a question anymore of, is it? Do we need to believe in it? It's happening. It's real. Now you just argue about how it's happening or why it's happening. So again, if you missed it when I was talking about it or you didn't think necessarily to be relevant, we're talking about lithospheric plates, not continental crust anymore. It's lithosphere. And it is broken into pieces like plates. Picture an egg being dropped. And you're going to have big pieces, you're going to have little pieces. That lithosphere is resting on the asthenosphere, as we said earlier. And what you hear about are the plate boundaries. And again, not everyone is following through as much as the next person. Plate boundaries, those are the seams. That's where one plate ends and another plate begins. Okay? They're little gaps. Depends if the thing is pulling apart, going together. Like I said, we don't need to worry about that. There's a half a dozen different ways they could interact. But where they interact, where we see the earthquakes, where we see the volcanoes, where we see the mountains, that's all on the boundaries usually. Not always. Hawaii's in the middle of a plate. It's not because of plate boundaries. It is still plate tectonics, but... So here's our plates. You don't need to memorize these. Just want to give you an idea of what we've been talking about. Roughly speaking, they're your continents or your big oceans. The Pacific plate is basically just the Pacific Ocean. The North American plate, mostly North America, got a little bit of the Atlantic Ocean on it. The Eurasian plate, most of Asia and Europe with a little bit of Atlantic Ocean on it, so on and so forth. And like I said, some of these plates are moving towards each other, some are sliding side by side, some are pulling apart, and that's where all the stuff that gives you an entire chapter to talk about comes into play. And again, we don't necessarily know why North America's moving northwest and the Pacific Ocean's moving in a different direction. Because after thousands of miles of those little convection cells turning one direction, why all of a sudden do they decide to start turning another direction? So, plate tectonics. And as I said, this is important because responsible for things like earthquakes, volcanoes, mountains, many mountains, not all mountains. The current location of the continents plus the past and the future, obviously. And that, my friends, is the end of this segment. Switching gears one last time, we'll come back on Tuesday to talk about the last section of this. It goes back and talks about the evolution of the Earth. All right, from it coming together to life, and then we'll pick up with how life has changed the planet, which is environmental science.